forms. Okay, you either get the percent by mass or the percent by volume. Those are really your only two options. Okay, as far as at least chemistry goes. Percent by mass means you have enough information with just a given formula to be able to predict that out. Percent by volume, we'd have to give you a whole lot more information. So if you're being asked for a percentage of really anything, as far as the final goes, you're going to be asked the percent by mass. Okay? So if we're looking to set this up to solve, okay, we want the percent water. Whoops, come on, pen. Water in borax, which is really a fancy way of saying I want the mass of water over the mass of borax times 100. And I now have my percentage. All right? So where do I find the mass of water? Okay. So what we're going to do is pull that information off of our periodic table. And we're going to have to be a little bit careful with this, which we'll see here in a second. So we can go to the periodic table and pull the mass of water. We know the formula for water, hopefully, is H2O. So we've got 2 hydrogens, 1 oxygen. Hydrogen comes in at a mass of 1. Oxygen comes in at a mass of 16. So we're looking at 18 grams of water. Is it only 18 grams of water in borax, though? Okay. Because we've got to go back and look at the formula. We're looking at where water appears. Is it saying I only have 1 water? No, it actually says I've got 10, which means that 18 grams needs to be multiplied by 10. Okay. That's now going to get me the mass of water in that sample. To determine the mass of borax, I do a very similar process. I would look at the mass for sodium, 23, close enough. 23 grams, officially again per mole, but there's 2 of them, so times 2, plus boron, probably 10.81 makes a little, or 10.8 makes more sense than using 11 grams. How many borons were there? 4, plus the mass of oxygen. Oxygen was a 16, times how many?
7.
Okay. It is going to come up to how you want to address this. It could be either 7 or 17, because the oxygen does also show up in the water. That's part of that formula. So it's up to you how you want to kind of break that down. I'm going to go ahead and say by 7, and then I'm going to say the mass of water, which was 18, times 10. Right. Now it's a question of doing all that math. Right. Lots of addition, multiplication stuff, so I would probably go through and break this down into individual steps. The top one I've got pretty straightforward. The bottom one I would need help on, and I'd actually have to go through and use a calculator for. Do you guys want actual answers? Yeah? Then I need a number. Said 4.2? Officially, and I always forget to deal with it, you have to drop in that times 100%. So 180 divided by 381.42 times 100 is 47.2%. Okay. At this point, we're relying on one person's numbers behind those calculations. Ideally, somebody else confirms so that we actually know that those numbers are correct. Yes, Eden? So on the top, we're concerned about the amount of water that's in that substance. Okay, so it has to show up on top. Okay, that water is part of what makes it borax. So it's also in the borax thing.
What's that dot in between
Which brings in a different comment. That dot is a way of saying that those two formulas are tied to each other. You can't break them apart. Okay, why would we include that dot? Because if I didn't include that dot, I could end up with this formula. Technically, I think we had to go H next. 17. And if I gave you that formula for borax, how much water is there?
None.
that becomes the problem. Okay? If I write out the formula in that format where I just look at the individual elements, I can't see how much water is present. Okay? So there are certain compounds where what we'll do is show that it's technically a compound of compounds. Okay? So that borax requires all of those pieces, and when we look at those pieces, water is in there as its own set. Okay? So this dot is typically used for what we know, or what we would call hydrates. Hydrate meaning, water is present. Okay, so that dot just means that they're tied to each other. Does that help answer your question, Eden?
So like aqueous?
It's not aqueous, which is the other thing that's kind of confusing on this. You go, well, if there's water present, it must be dissolved in water. It's not dissolved in water. The water is part of the crystal structure. Okay? To kind of help as a different example that you might be familiar with, if you've seen salt shakers, everybody's probably seen a salt shaker, right? And you can shake and salt comes out of it. You might have heard of or seen people have, the first time I thought, just walk through how I saw it. I was like, why the hell are there maggots in my rice or my salt? This is really, really gross. What's going on? And upon closer inspection, it's not maggots. It was rice kernels. Why are people putting rice in their salt?
Because it absorbs moisture.
The rice will absorb the moisture from the atmosphere instead of the salt. It's not something we typically do in Arizona because we're dry. There's no moisture in the atmosphere. But if you move to any of the coastal regions, okay, what you will sometimes see is even restaurants will have rice in it. And that's because what do you want to have happen when you shake your salt shaker? Salt comes out. If you don't have the rice in there, the salt will absorb that water. And when it absorbs that water, instead of being these nice small grains of salt, it turns into large chunks of salt. The chunks won't come out through the tiny little holes. Okay? So it is still a solid, it's just a larger extended structure. Right? And so that's what's happening here. It's not aqueous, it's still a solid, but the water is in a coordinated fashion with the overall structure. Kind of make sense? So that should answer your follow-up on it. And are you good with that? Okay. Did we get confirmation with that number?
Yes.
Okay, just checking. Next question.
64.
Probably one of my favorite questions. So with 64, we're looking at these formulas, and as soon as you see those formulas, what thought do you think should be going through your head? There are a couple perfectly valid, correct answers to this. The double arched rainbow thing, okay, I accept that. What's the double arched rainbow thing talking about? Okay, it's talking about our forces. Okay, so it's the application of our forces into physical properties. Okay, so that's where this should be going. The other thing that it could be going is this means I'm looking at structural formulas and I'm not confident in structural formulas, which means you could say study it. What if you're on the exam? Skip it. Move on. It's going to cause problems. Just move on and see what you can come up with later. Okay? And so we'll look at a couple different strategies to help work our way through this. First and foremost, what we should start with is what the appropriate approach is. So, based only on intermolecular attraction, formerly known as forces, predict which of the following liquids has the highest vapor pressure. Okay, so we want to be able to tie down some of this information. Okay, do you know what vapor pressure is? And so for the people saying yes, I'm not talking to you. For the people that are saying no, we need to come up with some way to understand what's going on with what vapor pressure is actually referencing. Okay? You have to know some content, but it's a question of what content can you rely on. So when we're looking at that word, we won't worry about highest, we'll be concerned with vapor and pressure. What is pressure? Or maybe a better phrase would be, when is pressure? The amount of force, something's pushing on something else. Good. What's the something? Okay. And here becomes the fun part. When did we talk about pressure? We only talked about pressure with gases. Right? So if we're now looking at this, if we're talking about highest pressure, so if pressure means gas, if we're saying highest gas, we're saying which of these is most gas? Okay, but they're liquids. So how many of them should be gases? None of them. Okay? So really what we're asking about is we're looking at what is the transition between our liquid to gas. Well, what controls the transition to liquid to gas? Okay, and this becomes interesting. Temperature isn't the thing that controls it. Temperature is the thing that affects it.
The speed of the atoms banging against each other.
What's even controlling? That's just raw energy of the system, and the temperature is also a measure of that energy.
How strong they're connected.
That's ultimately what it's coming down to. When we're looking at a phase transition, it's how are the individual molecules holding on to each other. So if we're looking at this liquid to gas, okay, our answer needs to be most gas. Okay? To be most gas, what has to happen to that transition point? That temperature should be the lowest possible, okay, because it's breaking what kind of forces? It needs to be the weakest possible forces. We'll come back to you in a second. You answered the next question. So if we're looking at the most gas, we're looking at the weakest force. The weakest force, according to our rainbow, is our London dispersion force. But when we go through and look at our answer choices, none of them show the forces. So it's not just knowing the force. I also have to know where the force comes from. So I'm not looking for London dispersion. I'm looking for, someone was saying it, nonpolar covalent. Nonpolar covalent bonds. All right, which then pushes the next question. How do I know I have nonpolar covalent bonds?
Hydrogen, carbon.
Cool. I'll accept hydrogen with carbon, and then
Two of the same atoms.
same to same. So really what this question is asking is, do you have that? That's all you need to go through and evaluate. All. Okay? To get to that point, you had to follow through all of those other logical steps that we just navigated, which is why I like this question. You have to think and reason through multiple tiers of things to get to what ultimately is the underlying question. Okay? So now what do we go through and do? We look at each of our answer choices. Which of them is hydrogen to carbon or same to same? So if we started off, answer choice A, what do you see? Hydrogen to carbon. Okay? And I like what you said. I like how you said it. I don't like what you said. Okay? Because you said hydroxide. There's no hydroxide. The only way I have hydroxide is if I have an ionic bond, that's a metal and a metal and then the OH hydroxide ion. Okay? I don't have hydroxide here because I don't have the metal. What I do have, you could go through and say the O and the H, but I would argue the more important thing is to acknowledge you have O. And actually we'll lean a little bit more into that. We do need to talk about the H, because when we're trying to identify our nonpolar covalent bonds, we're looking for hydrogen to carbon and same to same. So oxygen to oxygen, as the formula suggests, which is horribly wrong for the record, would look like a nonpolar covalent bond. That would fit our category. Okay? However, the O to H, that is not a nonpolar covalent bond. Right? And if that is not a nonpolar covalent bond, what does that mean? And you can get into what it means for that structure, but that's not what the question asked. The question said, I need to find Hydrogen to carbon are same to same. And if I have oxygen to hydrogen, it's not the answer. I don't care that it generates hydrogen bonding, necessarily, right? But I know it's not the answer. I look at answer choice B. What do I see? Just carbons and hydrogens, which would suggest those are all nonpolar covalent bonds. How tricky did this question get? It didn't get tricky. Okay, good. Okay. So, based off of the work that we followed, what have we just discovered? The answer. Okay. Because we're not on an exam, let's look at the rest of the answer choices. What do we see in the next one? I see an oxygen. An oxygen bonded to either carbon or, pains me to say this, hydrogen. It's not bonded to hydrogen, but oxygen to carbon or oxygen to hydrogen. Either way, is that nonpolar covalent? No, which means wrong. How about the next one? This one gets harder, and a lot of people will miss that that's a chlorine sitting out there. That chlorine, at best, we'd be saying, or at worst, we'd be saying it's bonded to that hydrogen. That's not nonpolar covalent, which means not the answer. What about the last one? I see the sulfur chilling in the middle of that formula, which again means not nonpolar covalent, also wrong. Kind of, sort of? Yes?
If the sulfur wasn't there, and it was just like polar covalent, which one would be like the higher favorite?
So what you're asking is if I make this last one CH, just do that? Okay. We're going to cross that bridge in a second, but let's not do that yet. Okay, let's go back and say your content knowledge was this. Okay? So you look at this, I have no idea what vapor pressure is. Okay? Even saying forces is kind of questionable. Okay? We could probably even delete that. Can we reason our way through based off of the answer choices? Okay? So what we would try and do is look at each of those answer choices and say what stands out as uniquely different. So what stands out as uniquely different in A? Okay? I have an OH. Okay? And we might even lean into and say I have an O. Why is O uniquely different? What makes O special from everything else? This is where having certain trends from the periodic table becomes really, really important. Oxygen is the second most electronegative element on the periodic table. So oxygen stands out as uniquely different just within that formula because its electronegativity is way different than everything else. If I go through and look at answer choice B, what do I notice? Answer choice B is all just CH3s. So we could go through and kind of color code if we wanted. What happens when we look at C? Ooh, I see another oxygen appear. Okay, what happens when I look at D? I see that chlorine. What do I know about chlorine? It's also very electronegative. Last one. Sulfur. What do you need to do to answer a question? You need to find the thing that is uniquely different from everything else. What answer choice is uniquely different from everything else? Why is that the answer? No clue, but it stands out as something uniquely different. This approach doesn't always work, but what you're looking at is trying to find patterns and hope for the best. Does that make sense? Okay. So, because Eden asked it, let's go ahead and just make life miserable. And say we encountered the new question where it came in as this. Okay? If we go through and do that, hopefully we can eliminate answer choice A, C, and D. We're going based off of our actual content knowledge now, the stuff that I've all deleted. And we now have 2 answer choices. Okay? 2 answer choices that match the nonpolar covalent choice. Okay? Which one is going to be most gas? Either. Most gas between these two, so it's relative. Okay. So it's fun. E and B sound really similar, so let's switch that up for my good old deaf ears. A and D sound different. Let's go with that. So which is a better answer choice, A or D? So we're seeing some A's, hearing some D's. Okay? And this does become a whole lot more challenging to deal with. What we're talking about is the forces. Okay? Well, the strength of the force in both cases is spot on identical. They're both London dispersion forces. Okay? But is there a difference between them? Yes. One is smaller, one is larger. What does that mean? There's more particles or more space in A. Why does that matter? If there's more space in that individual particle, I can stack more things on top of it. So the analogy that I usually use, which I don't know if it made it into the video or not, is that if we take 2 particles and we look at the surface contact between the sheets of paper, right, those 2 have a lot of surface area contact. Right? Each of those places of contact is an attraction between the paper. Right? But if I go through and crumple them up into tiny little balls, and I now look at where they make contact, are they making contact in as much a space? No. Right? That fewer spaces of contact means I have less potential interactions. Less potential interactions means really easy to go up into the gas state. So structure D is going to have a much higher vapor pressure than A, right? Because it has less potential to make the interactions between those 2 substances. Right? That, I think, is an important discussion, which is why it's in the lecture videos, which is why I appreciate that you asked that question. How important does the rest of my chemistry colleagues think it is? That's an appropriate response. They don't think it's valuable to discuss right now. Right? And as such, when you go through and look at the questions that you get are not looking at, come on now, let's try that. They aren't looking at those nuances of the amount of the force, they're only looking at the raw strength of the force. Right? So they're kind of 2 stages of thought. Does that make sense? So your question, Eden, that explains it. Do we need to worry about it for the final? No. Right? If for whatever reason you need more chemistry, a lot more chemistry, this concept would show up again in organic chemistry and it would get developed more to the point where you realize that they're pretty hand-wavy arguments at best. Okay? And they're very, very, very complex. And we have to narrow things down to just looking at 2 structures, and it's always a relative thing. I can't look at an individual molecule and say, ha, it's going to have a melting point of 400 degrees Celsius. We don't have that ability. What I would do is look at 2 different structures and say that one is larger than that one. I don't even know what the numbers are. I just know it's bigger. That's it. Okay? Which is lovely. Here's the pitch for OChem. We don't worry about numbers. Yay. You just have to worry about structure. Okay? Questions about that one? Next. So, what is champagne? A liquid. Okay? Okay, and if we buy champagne, we're talking about it being in a bottle, right? There's our liquid. Okay, and of course we put a fancy cork in the top of it. Okay, and that cork gets wired down, fancy wired down. Okay, and while our champagne is here, what's up here? Gas. What gas do we want that to be? That should be our carbon dioxide. Because what we're trying to do is force that carbon dioxide gas to be where? I want to get that gas to go into the champagne, which is a liquid. So really what I'm talking about is what is necessary to make a gas turn into a liquid. That's what the question asks. Okay? We could talk about a variety of different things that can control that, but the question is narrowed because it's now having you look very specifically at two factors: pressure and temperature. Take your pick. Temperature. Temperature is probably the easiest of those two. To get that gas to turn into a liquid, what do I need to do to the temperature? I need to decrease it. It needs to get colder, right? Okay. I have to cool that down. Okay. So typically when we talk about champagne, what temperature is it? It's served usually on the cooler side. Depending on hoity-toityness, you can make adjustments, but it's definitely not served hot. Okay? If you're like, well, I don't know a whole lot about champagne. How about your soda? It's the same principle. Okay? We have a liquid, and we have CO2 above it. You're trying to get the CO2 into the liquid. That's it. And when you think about your soda, why do you not heat up your soda?
Because that's nasty.
What's that? All the bubbles disappear. Why? Because when you add that heat, what are you helping to do? Transition from the liquid to the gas. All the bubbles leave the system. Okay? And if you're like, that's gross, have you had Kool-Aid? Is Kool-Aid gross? Kool-Aid's not gross. Give me a break. At least I'm not referencing Tang. Nobody knows what Tang is anymore. Tang is fantastic. But unfortunately, we've just dated ourselves. Okay? So if we're looking at that system, we want a temperature that's very low because I'm trying to force the gas into the liquid. Okay? So I could go through and look at my answer choices. Temperature is not a factor. Yes, it is. Low temperature, good. Low temperature, good. Low temperature, good. High temperature, bad. Okay? So that's cool. If that's all I've got, you've went from a 20% odds to 30% odds. That's a pretty good swing. Okay? For knowing one piece of information. The other part of this is now going to come down to pressure. Well, when do we use pressure? When did pressure as a concept come about? When we talked about gases. Are we talking about gases here? Yes. Which means, is pressure going to be important? Yes. Pressure is not a factor is now a wrong answer. Okay? Now we've got to consider how can this pressure help us out? Okay? Well, if I consider the gas, and I just have this box and I have gas, it's everywhere, right? And I have that same box with that same amount of particles, where's my liquid? Okay? It's not occupying the entire volume, it's all smushed down at the bottom. Okay? So if I'm trying to make my gas look like my liquid, what do I want to do to those gas particles? I want to push them to the bottom of the container. You mean I need to exert some kind of pressure to force them into that system? Yeah. So to force the gas into the liquid, what do I need to do? I need to increase the pressure. I have to put an external force to force those gas particles to stop moving. Low temperature, high pressure. Does that kind of make sense? Okay. If we try to do test-taking principles on this one, this is not a great one to do it with because we have pretty much every permutation possible within this. So there isn't a whole lot you can rule out. You're stuck either knowing the content or not. Okay? And in most scenarios, it is easiest if you take it out of the context of the specifics and make it more general. Gases and liquids, simplify. Okay? You could push on this even further and say, well, okay, champagne I don't know a lot about, but I know it's got bubbles in it. Ooh, my soda has bubbles in it. You remember the last time I left that can of soda in my car in the middle of the summer? What happened? It exploded. Well, what's happening in the middle of the summer? It's hot. Is hot keeping the gas into the can? No. Hot is pushing out on the gas. I'm getting more gas. I have a closed container with a rapidly expanding gas known as a bomb. I can leverage that. Okay? And I can use that information to help me kind of reverse engineer and think through this. That requires time. And so if you're seeing a question like this that you're like, ugh, I don't know this instantly, move on. Don't sit there and spin your wheels on it. Okay? Move on, double back to it when you feel you've answered all the ones you know, then you can double back and start to reason through.
Can you explain why when we get a cold soda that it expands?
Okay? So a cold soda, does the cold soda expand? No. Cold soda isn't expanding. What you're referencing isn't a cold soda. What you're referencing is the soda that I put into the freezer and I forgot about. And that then exploded on me. Okay? That becomes one of the challenges within this because that seems to run counter to that principle. There's another factor going into that. Okay? When you see ice, where is ice? On the top, because ice is less dense than the liquid. Okay? Ice, for the same amount of same amount of substance, occupies a larger volume. So when I'm looking at that soda and I put it in the freezer, it's not expanding because of the gas and breaking. It's expanding because the solid ice takes up a larger volume and the solid is actually breaking the container open. Okay? That then causes other messes because it probably wasn't fully frozen and yeah. Okay, but that's what's happening there. Which, interestingly enough, is one of the reasons why we tend to expect or predict that we get life, is because of water and some of the weird properties of water. Most solids do what? They sink. Okay? They typically occupy a smaller volume because the particles are closer together. Water's a strange molecule indeed, because when we actually make it into a solid, it arranges itself so that it occupies a larger volume. That larger volume puts ice on the surface as opposed to underneath. So if we had an ocean of a different material, where would the solid form? It would form on the bottom of the ocean. Right? And now we've got a problem because that doesn't get any heat. And so eventually what's going to happen is your whole ocean would then be all solid. And now you don't have a liquid to allow chemistry to actually happen. Because we have ice on the surface, you can still get liquid and chemical reactions happening under the surface. Which is kind of neat. Water's got all sorts of fun properties, but that's a different class.
For this question, you have write the formula of E equals to NR in the arrow.
Could you also go through and use PV equals nRT? Yes. Okay. And I totally agreed with you, and then I totally spaced on how I would approach it. The issue there is all you'd be defining is the relationship between the pressure and the temperature. So if I increased the temperature, what has to happen to the pressure? Okay? And this is where people go up or down. Let's say there were ones. Let's increase the temperature to 100. What had to happen to the pressure? It decreased. So this was 1 over 100. Is that an equality? Nope. For it to be an equality, what had to happen? It also had to increase. The only place you get that inverse relationship is when they're on the same side, so moles and temperature are going to be inversely related, Or when you look across the equality, and you can see it if we rearrange Pivnert, come on. If I see temperature in the numerator, equality, and then my moles in the denominator, they're inversely related. But if I'm looking at temperature related to volume across an equality and they're both in the same space, they're directly proportional. When you increase one, the other one must also increase. It's only when you flip across that fraction. Kind of, sort of? So in shaking your head to that, which is okay, did you like the earlier explanations?
Mm-hmm.
Stick with those. Next question.
66.
So just a quick glance at the question, what do you see? Say again?
Like dissolves like.
Okay, we're seeing like dissolves like. Okay, what else do you see? What did you mouth? You got missable? Okay, I'll tell you, genuinely I don't think you should be doing this, but it's hard to not do it. You'll see the answer choices, and I immediately see all these formulas. Okay? I see all those formulas, and I immediately think, I'm going to be interpreting forces. Okay? That's going to have to come out of this, because I'm now looking at how those formulas are going to somehow do something in the question. Okay? So let's erase all that content, because theoretically we shouldn't be there. So the first thing that was mentioned was like dissolves like. What is like dissolves like talking about?
Space. State of the substance.
Phases, sort of. Say again? Okay. This can go back to the concept of bonds, but we have to be a little bit careful. When we're talking about something dissolving, are we breaking bonds? I have a new thing. I have sugar water, which means that I break the bonds of sugar. No, otherwise, I wouldn't still have sugar left. Okay, all I've done is broke something else. What did I break? I broke the forces. So the structure itself still is integrated, still exists, intact, thank you. Okay, so we're talking about forces. Okay, I would argue that when you see like dissolves like, okay, a better expression for it would actually be like forces dissolve like forces. So what I'm asking is, do they have the same force? If they have the same force, I would predict them to mix. Okay, what's them? What's mixing? Just kind of getting at to what dissolves is referencing.
Solubility.
So we could go with solubility. What does solubility mean? Homogeneous mixture is talking about that too. What does that mean? Something dissolves in something else. That's what our solubility is talking about. That's the homogeneous mixture we're talking about. Okay, the fancy words we would use is a solute dissolves in a solvent. Okay, so when we're talking about like forces, it's the forces of the solute dissolve the forces of the solvent. So I have to know the forces for two different states. Okay? My answer choices are going to give me one of those, either the solute or the solvent, which means the question must be giving me the other one. So I've got to go through the question and read that really carefully to make sure I know what the other one is. What is the other one? Water. Water is our solvent. That would be H2O. Okay, again, that's a formula you're expected to kind of know as common knowledge. There was reference to miscibility, which I understand and appreciate why you would use that. Miscibility is really just a synonym as far as you're concerned for solubility. Solubility describes anything dissolving in a solvent. Miscibility is talking about a liquid dissolving in a solvent. So it's a narrower definition. As far as you're concerned, it's the same thing. Right? So if we're talking about applying like forces dissolve like forces, the very first thing we should do is determine the forces on the substance that we know. We know we have water, so what are the forces in water? Right? Because there was enough pause with the question of what are the forces in water, what we're going to have to do is take it a step further back, because when we're looking at the formula doesn't show us the forces. What it shows us is the bonds. So what are the bonds present in water? And now your answer is correct. We're now looking at polar covalent. I would perfectly happy with just polar as well. Okay? And if we have those as bonds, what does that turn into as far as our forces? This would be our dipole-dipole. You can use whatever notation you want as long as you know where it's at within that ranking system. Okay? It's multiple choice. The only place where you would get in trouble for calling it DD is if you didn't know it meant dipole-dipole and we didn't write dipole-dipole, or we didn't write DD. Okay? So cool. What does that mean we need to do? We now go to our solute and say which of our solutes gives us dipole-dipole. And we'd be done. Okay? Except what we're going to do is play this a little bit softer, and that acknowledge that when we see a dipole-dipole force, we should immediately also consider, is there potential for something stronger than dipole-dipole? Okay? Dipole-dipole is a broad class that does have a secondary classification associated with it, and that is hydrogen bonding. So as soon as I see a dipole-dipole, I should ask, do I have the potential for hydrogen bonding? How do I know I have hydrogen bonding? Is there a hydrogen bonded to NO or F? Okay, so in the case of water, yeah, there is, which means the force that I'm looking at isn't dipole-dipole, it's hydrogen bonding. That's my primary force. Okay? I still have dipole-dipole, but hydrogen bonding is the stronger force, which goes all the way back to where we started with Eden's question. Our primary focus is on the strength of the forces, not those secondary effects. So we'll start with hydrogen bonding. We can now go back and look towards our answer choices, okay, and look for hydrogen bonding. Problem with looking for hydrogen bonding, that's a force, which is never shown. Okay? So we've got a good thought process all the way down, but what are we going to look for?
Bonds.
The bond, and in particular, a polar covalent bond. Okay? We might acknowledge the polar covalent bond is only going to take us to the dipole-dipole, so more than likely an even better bet is, do we see a hydrogen bonded to oxygen, nitrogen, or fluorine? Okay? If we got that, that's going to be something that should mix at a first approximation. Oh wow, it's way up there. So we can now go through and look at those structures as we remove some of that. C5H12, I don't see any oxygens. C6H12, I don't see any oxygens. C6HCl, I don't see any oxygens, nitrogen, or fluorines. Okay, I might pause on that one because I do see a chlorine. Okay, that chlorine could shift me into a dipole-dipole. I move to the next one. I see oxygen and a hydrogen very clearly shown bonded to it because it's within the parentheses. That screams at me I've got an answer. I look at the next one. That's all carbons and hydrogens. Cross that one off. Two answer choices. One of them stands out as the extra fit to match the hydrogen bonded to nitrogen, oxygen, or fluorine. Kind of, sort of? Ashley, was that yours? You good? Anybody else have questions about what's up there? Okay. Again, future classes can make this more complicated. Right now, find your strongest force, match the strongest force. Okay, that's what dictates the overall properties of the molecule. Subtle extra thing that we can address, which is more clear here. Okay, if we have hydrogen bonding, we have dipole-dipole. Do we also have London dispersion? Yes. And you're like, but that's only for nonpolar covalent bonds. No, nonpolar covalent bonds can only have London dispersion forces. But London dispersion is really just talking about where the electrons disperse. That's the D part of dispersion. So any molecule that has electrons has London dispersion forces. How many molecules have electrons? Every single one. Okay? So the dispersion force will happen for all molecules. It just happens to be the weakest force, so we tend to ignore it. Kind of makes sense? Okay. Oh, I can't scroll down any lower. 68. 68's a fun one because it's very similar. Okay, we're following the same patterns behind it. And I would argue the breakdown that we went through and did with that first one sets us up. Our like dissolves like was talking about the forces, okay, of our solute being similar to the forces of our solvent. Okay, that's our big deal. Okay, so if we're going to have something dissolve, those forces need to be the same. Okay, what's our solvent in this case? Which is a little bit unfortunate. The solvent is the answer. Okay. So what's the solute? That's our bromine. So what we've done is kind of flip this on its head, and we now want to look at the solute forces for bromine. What kind of bond do we see in bromine? Okay, so we're hearing a couple different answers. Some of those answers are actually correct, and some of them are challenged for different reasons. Okay. One of the common mistakes is people will go through and look at bromine and go, oh, bromine's electronegative, so it must be a polar covalent bond. What's it bonded to? It's bonded to bromine. Okay? So I don't care that it's electronegative. What I care is that that is same to same. And same to same is nonpolar covalent. That nonpolar covalent bond is going to lead me to London dispersion forces. Okay? So what we'd be looking for is, again, compounds that match London dispersion forces. And for those of you that are reading carefully, I'm aware of it. We're just moving as we move. Okay? So if I now want to think back to what I want to fish through answers, yes, I want London dispersion forces, but I can't see those forces, so I have to recognize that what I'm answering is actually that I have nonpolar covalent bonds. I'm looking at same to same or carbon to hydrogen. Okay? So I can now go back to my question and look at my answer choices, and this might give me a bit of panic. Because I look at answer choice A, I see carbons to hydrogens, and that's it. That fits nonpolar covalent. Ta-da, there's the answer, but wait. So's the next one. And so's the next one. So how could I possibly differentiate between three different answers? Okay? This will happen. You'll get a spot where you're confused and be like, I can't tell the difference between which one of these answers is correct. Okay? At that point, two things should potentially happen. If you've written work, there's already work there, you can move on and you can restart at a different point. Okay? Because you've hit a wall, move on, come back to it later with a fresh brain, and hopefully you'll break through the barrier that's preventing you from answering or differentiating those answer choices. Okay? The other approach, you're brute force, you're sticking with it, and you're going to try and slam at that question and hopefully see what you missed. And if we go through and read the question really carefully, apply the like dissolves like rule, cool, to predict which of the following is not a good solvent. Everything I answered was for it to be a good solvent. So I misread the question and lost the not. Okay? Different test-taking designs and implementations behind this. Okay? If you go back and look at our exams, okay, usually I try to capitalize nots or bold it or call attention to it. I can't vouch for any of that within the final exam. Okay? I was the one that compiled and put it all together, so there were things like that that I tried to catch, but I can't guarantee it. Okay? So make sure that you watch out for those nots, because those are going to mess with this. If we're looking at not a good solvent, what does that tell us right away? Those three are all wrong. Okay, so I went from not being able to choose between 3 different answers to now only having to choose between 2 answers. That's a pretty good win off of a simple fix to reading the question. Okay, but we now have a slightly more complex part of this. How do we differentiate between those 2 answers? Okay, if it's not a good solvent, what is that going to mean about the forces? Should they be like? No, they should be unlike. And if I'm looking at something to the extreme, I want to make it as most unlike as possible. What is most unlike nonpolar covalent bonding? Okay, so follow the rules, not the answer. What is most unlike a nonpolar covalent bond? An ionic bond. So where I want to fish for first is, do I have an ionic bond? Okay, and of course, for all everybody that was shouting out all the other answers, that's not our answer choice, so we can't do that. So what's the next most unlike? Dipole-dipole. And when I go through and look at these 2 answer choices, we again encounter a problem because they're both dipole-dipole. Well, does dipole-dipole generate only one force? No, it generates 2 forces. Okay? We have the blanket statement of dipole-dipole, and then we have the uber strong hydrogen bonding version of it. If I'm trying to find the most unlike, what is the most unlike force to London dispersion? Our strongest force, we already got rid of ionic. What's the strongest force between hydrogen bonding and dipole-dipole? Hydrogen bonding. Okay? So if hydrogen bonding is my most unlike, how do I know I have that? Well, it is a dipole-dipole, but it's a dipole-dipole and just a hydrogen? Crap. We'll fix this one so that I can break your... We'll go with chloroform, CHCl3. Still has a hydrogen. So hydrogen bonding is not just that I have a hydrogen. It's that hydrogen must be bonded to nitrogen, oxygen, or fluorine. Okay? So, which of those has a hydrogen bonded to oxygen, nitrogen, or fluorine? Water. Chloroform doesn't. It has the hydrogen, but it doesn't have it bonded to the proper element. Does that make sense? So you have to hold that definition for hydrogen bonding. It's not just the presence of hydrogen. It's that the hydrogen is physically bonded to nitrogen, oxygen, or fluorine. Make sense? So our answer is D. Okay. Why do I go through and solve it wrong? Because the first time I did this question, I solved it wrong. Okay. So you need to be familiar with how to break out of patterns where you're like, what went sideways? Okay. Karen, that was yours? You good? Other questions?
67.
So, what are you being asked to solve for? Molarity. What is molarity? So right away we should be moles of sucrose over liters of solution. That's what I want to solve for. I could now go through and look at the given information. I'm given a whole plethora of information. I'm given 10.0 grams of this goofy formula. Guess what that goofy formula, usually they tell you. What must that goofy formula belong to? That's got to be sucrose. They also tell me that 342.34 grams of sucrose is 1 mole, and immediately note that I'm writing that out in that fraction instead of using the stupid line thing. And then I'm also told, circled that poorly, that I have 100.0 milliliters of solution. So, what should I do? What do you see? Say again? Cool. You want moles of sucrose and you want it up here in the numerator? Okay, cool. Do you know the moles of sucrose? I like molar mass a little better. Okay. We do know from our given information, the green one doesn't have moles, the blue one doesn't have moles, the purple one does have moles of sucrose. But it's relating the moles of sucrose to the grams of sucrose. Yeah. So, I can now use my numbers, 342.34 grams is 1 mole. Cool, this has now brought in moles of sucrose. That's what I wanted, and I wanted it in the numerator. Fantastic. What else do I need to do? Right, you want to cancel out the grams of sucrose. Okay, do I know the grams of sucrose? Yeah, it's actually given to me right out of the question. I'm told I have 10.0 grams of sucrose. What goes in the denominator? 1. There's nothing else associated with that. It's a straight up just single measurement, grams of sucrose. So don't start manipulating it. What happens? Grams of sucrose cancel. Fantastic. Now what? Say again? You said liters? Cool. Our answer says we need liters of solution in the denominator, right? Do I know the liters of solution? No, what do I know? I know the milliliters of solution. Okay. Before we get excited and start writing 100 in here, that 100 isn't related to liters. That's, again, a single measurement in and of itself. So if I'm going to bring in that liters, as I have, that is now a new conversion factor. Where's that conversion factor? Say again? This is in your brain because you've been told that you need to... That says brain, not Brian. Okay? You need to have that memorized. This is the case where you need that. Okay? I always hate asking this question, but what have you memorized?